Hey there, class. I'm going to go over the exam 3 review today. So this will be, kind of the, boiled down version of what you need to know for the exam. So let's start going through it here. All right. Okay, so sorry, forgot to change that. Okay, check Learning Suite for these dates. So this is going to be Monday and Tuesday, August 3rd and 4th, and not in the testing center. It'll just be online like all the other ones. Okay, but the date is right. It's August 3rd and August 4th. Okay. So same as before, I do all the tests Monday and Tuesday. The final exam may not be on a Monday, Tuesday. I'll have to check that one. But this will be similar to exam 1 and 2, where it's on Monday and Tuesday. So this exam will focus on chapters 9 through 11.4. Again, there will be stuff from the first exam and the second exam. It won't be stressed, and it won't be like a question that just asks about a topic from the first or second exam. But you'll need to know the concepts from before in order to answer some of these questions. And I'll talk about what to focus on as far as what to know from the previous 2 tests for what to know for this exam. All right, so again, there's 25 multiple choice questions that are going to be worth 60 points. And then again, about half require calculations. And then there'll be short answer questions, which account for 40 points of the exam. And these are going to be, there's 4 questions, but 10 sub-questions. So it might appear as 40 questions on the exam, basically. But you've seen this before. So things you need to know for the short answer questions are going to be solubility rules. So basically, if you see salt, either, by looking at a salt, the formula or whatever, you should be able to say if it's a soluble or insoluble salt. Be able to write equilibrium constant expressions. And for the short answer question, the way I had to do it to be online is you'll have to do a few calculations using the equilibrium constant expressions as well. I'm mainly focusing on can you write them, and then I use a little bit of calculations to help me with that. Anyway, main idea is writing equilibrium constant expressions, but you'll also need to know for this exam how to plug in numbers into the equilibrium constant expressions and do calculations. And we've seen practice problems like that in the lectures and homework and stuff. And then be able to know the acid and base naming. So if you see a formula, be able to come up with the name, or if you see the name of an acid or base, be able to write the formula. And then be able to identify conjugate acid-base pairs from an acid-base chemical reaction. Okay. All right, so again, you can use the equation sheets, the same ones that you've used before on the other 2 exams. There's an equation sheet, a periodic table, and then one more sheet that kind of shows you the names of the different atoms. So those 3 sheets you can find under the exam info tab on Learning Suite under content. And then you can also use a calculator. Remember the honor code, just be honest, and there's no, it's closed notes, closed book, no neighbor, take it by yourself in a room in one sitting. Yeah, just like you would be in the testing center. Okay. You can also have, of course, like scratch paper and a pencil, but no notes or anything like that. All right, so previous topics that you'll make sure you want to know, you'll want to make sure you know. So if you haven't mastered these, I'd review exams 1 and 2 to get these down. When we're doing calculations, knowing how to do significant figures, scientific notation, and the prefixes for, like milli and kilo, and then being able to use conversion factors to do unit conversions. be able to name and name ionic and covalent compounds and come up with formulas. For example, what you might see on the test, at this point, it's just going to say barium reacts with oxygen to form barium oxide. So you would need to be able to come up with this and then also balance the equation just from these words, okay? And then I would, the questions on exam 3 aren't simply going to be this because these are topics that we've covered before, but I would write this in the question and then ask, something else about it. So anyway, make sure you can do that. And then, yeah, obviously you can't balance the reaction correctly if you didn't come up with the correct formula in the first place. So you need to be able to come up with ionic compounds. Okay. And then from chapters 7 and 8, so from exam 3, balancing chemical equations, stoichiometry, mole ratios, molar mass. That's all the stuff we did in exam. Sorry, this is exam 2. Know if a reaction is endothermic or exothermic. Positive delta H means heat is absorbed. So that's going to be endothermic reactions, and heat is a reactant, right? This stuff. Ideal gas law is one that you'll need to know also for the exam. Okay. Okay, so now we're moving into content that we're going to focus on in exam 3. So starting in chapter 9. So we've definitions you'll want to know is what's the solvent and what's the solute, right? This is almost always water in what we do, and the solutes are generally salts that get dissolved in the water. Saturated and unsaturated solutions. Solution, colloid, suspension. We didn't focus on this a whole lot, but just know the definitions of these. They're pretty, it shouldn't hopefully take too long to look up those definitions. That's not going to be a huge point in the test, but you should still know it. Electrolytes, be able to determine if something is a strong electrolyte or a weak electrolyte. Again, strong electrolyte means it dissociates in water or is soluble in water. And then weak electrolyte is something that does not dissociate in water or is not soluble in water. So this would be like soluble salts and strong acids and bases. And then if something isn't soluble and it's not a strong acid or a strong base, then it's going to be a weak electrolyte. Okay. Solubility. So solubility increases with higher temperature and gases decrease with the higher temperature. We've talked about these two trends. Okay, and then Henry's law that basically says the solubility is related to the vapor pressure of the gas above the liquid. Just kind of know the definition of that there. And I think there's a couple equations that I think they're probably on your equation sheet. So I would make sure that as you're studying, like print out those equation sheets so you know what will be with you on the exam, and then you know what you need to study or memorize as well if it's not on the equation sheets. So this is the equation for Henry's law, and then there's a constant too, and I think all this is on the equation sheet. Okay, solubility rules. So there's been a little confusion with that chart. I think it is a little confusing. But there are multiple sources, like I've said, to find solubility rules, and all of them are just a little different. Different people like different ones. Here's another one that I thought I'd bring up in this lecture if you didn't like the original table. If you like the original table, you're comfortable with it, just stay with that. Doesn't really matter. Here's another way you can look at it. So basically, in order for something to be soluble, it needs to be on this list. So the way this one works is if it contains any of these positive ions, then it is soluble. If it contains any of these anions, then it is soluble. If it contains any of these, it's soluble except when, exceptions. And then sulfate is soluble except when, all these exceptions. Okay, so another way another table that you could use for solubility rules. So salts are, unless they're on this, they're going to be insoluble. Okay. All right. So you need to memorize these rules or memorize a different set of solubility rules if you want, as long as it's from a credible source and it's accurate. But there's a lot of different good like mnemonic devices or ways to memorize these online. So if you don't like any of the ones I've presented, you could look for some other ones too. But I would spend a lot of time going over them if I went through all the different ways that people memorize these. Okay. All right. So the reason you'll need to know these, there's two different situations. I might just give you a salt, right? I'll give you like sodium chloride or some other salt, ionic compound, and ask, is it soluble? And then the other time is when you do double replacement reactions and like net ionic equations, and need to know, is a solid formed in the reaction? Okay. So here's an example. Here's some examples determining if these are soluble or not. So if we look at chromium hydroxide, you can see that neither chromium nor hydroxide are on this list for soluble ions. So it's going to be an insoluble compound. Chromium and nitrate. Nitrate is soluble, so that one is soluble. Nickel chloride. Chloride is soluble, except with a few exceptions, but those don't apply here because it's nickel, so it's soluble. Anyway, you can go through and practice some of these, but some examples for solubility. The other time you'll need solubility rules is when you're doing double replacement reactions like this. So you hopefully are comfortable at this point, but if you need to draw the products or predict the products of this reaction, lead, here it's combined with nitrate, so now we're going to combine it with the chloride. And nitrate is a -1 charge, and there's 2 of them, so that tells me that this is a lead with a 2+ on it. So that means I need 2 chlorines for this. Then I would get sodium nitrate as the other compound. And then you'd write the phase. So chloride is soluble unless it's with lead 2+. So this is going to be a solid. And then this one is has sodium, so it's soluble. So this is aqueous. Okay, so that's where you would also need to be able to determine solubility rules. And then of course the net ionic equation is where you take the full equation, you split it up into all the aqueous molecules split up into ions. If it's a solid, then it doesn't split up, and you cross out the like ones and you combine them in the end and you get your net ionic equation. Sorry, that was a really fast explanation, but we dove into this deeply in the lectures, so make sure to review these if you're still having trouble. This PowerPoint, I'll go through some examples, but again, if you have any like deeper questions, come visit me during office hours or revisit the lectures where I go in more depth on how to actually do these problems. Okay, so units for concentration. So we had solubility, and remember this is like the maximum amount of solute that can dissolve in, here as an example, in 100 grams of solvent. Okay. Equivalence, so this is an equivalent is 1 mole of positive or negative charge. So like 1 mole of sodium plus would be 1 equivalent. 1 mole of calcium 2+ is 2 equivalents because that's actually 2 moles of positive charge, and so on. Okay. No percent volume, percent mass over volume, and molarity, which is, as you've noticed, the one that we use most often, which is moles of solute over, moles of solute for every 1 liter of solvent, or for every 1 liter of solution. Okay. And be able to use stoichiometry with this. I forgot to add the stoichiometry map on this lecture, but I will put it on the lecture before I post it online. So when you see this online, I'll have the full stoichiometry map up to this point, which includes using molarity and solutions in the stoichiometry problems. Okay. All right, so here's some examples. So let's say the question says, what's the concentration in milliequivalents per liter for 0.29 grams of sodium chloride in 200 milliliters of water? All right, so in this example, we can start with the mass of sodium chloride, convert it to moles of sodium chloride, and then we can say for every 1 mole of sodium chloride, we have 1 mole of sodium plus charge, and every mole of that is 1 equivalent. That gives us equivalents, then we convert it to milliequivalents, and that gives us 5 milliequivalents. And then we can divide by the volume in liters to get our final concentration. Now, this problem is a little confusing. It should say concentration in milliequivalents, like of positive charge. Okay, so I'll make sure I specify that on the exam. If you're confused, because equivalents could be positive or negative charge, but I would specify like how many equivalents of positive charge or how many equivalents of negative charge. In this problem, it doesn't really matter because sodium has 1 positive and chloride is a negative, is just a 1 negative. So if you did either positive or negative, then you would have gotten the same answer. But anyway, I'll make sure to be more specific during the exams. This other example is one like we've seen before. So this would be like a mass over mass percent, which is generally just referred to as percent mass. So an alloy of brass contains 65% copper and 35% zinc, and it tells you it's mass percent, which means it's mass of the solute divided by mass of the solution, or the alloy in this case. So this would be 100 grams of the solution. Basically, it says if you have 100 grams of brass, then 65 grams of that will be copper and 35 grams are zinc. Okay. So if a brass tuba weighed 50 pounds, how much copper was needed to make the tuba? Okay, so we start with or 50 pounds, which is 23 kilograms of brass. We can then, brass is our solution, right? That's the alloy, it's the mix of the copper and zinc. We can cancel out kilograms of brass using the mass percent, and it tells us how much copper is in that. Okay. All right. Finding concentration in molarity. Again, molarity is moles of solute over liters of solution. So we would need to find the moles of the solute first. So we can convert from grams of sodium chloride to moles of sodium chloride using the molar mass. And then we can divide by the volume of the solution to get our concentration. Okay. Another thing we talked about with solutions was changes in boiling point and the freezing point. So the boiling point increases when you dissolve solutes in water, and the freezing point decreases. Right? We had some equations here. So the change in temperature is equal to K, whether it's for freezing or boiling, times the number of moles of solute divided by the mass of water that you have. Okay. So for example, I'm about to get to an example, I think, but yeah, one more thing to remember is that you're using the total number of solutes. So for example, if you have 1 mole of sodium chloride that you're dissolving in the water, it's actually equal to 2 moles of solutes, and that's what goes in this spot for N when you use this equation. Okay. Calcium nitrate actually is 3 moles of solutes, and again, that would go in the spot for N. So here's an example. So you have the boiling point of water. What's the boiling point of water if you add 117 grams of sodium chloride? So we need to know how many moles of solutes there are. 117, let's see, yeah, 117 grams of sodium chloride. We use the molar mass to get moles of sodium chloride, and then for every 1 mole of sodium chloride, we have 2 moles of ions because we have a sodium and a chloride that come apart. So that gives us 4 moles total of solute. Divide that by the mass of water in kilograms and plug it into the equation. So this is K, and then we have N over M right here equals delta T. And that gives us the change in temperature, which we then either add or subtract to the original. If it's a boiling point of water, we add it to the boiling point to get the new boiling point. If it's a freezing point, we would subtract it from the freezing point, the original freezing point of water. So you should know those, right? Freezing point of water is 0 degrees Celsius, and the boiling point is 100 degrees Celsius. So we take 100, add 8.2, and we get the new the new boiling point for water. Okay. Osmosis, another idea we talked about. So this is where water can move through semi-permeable membranes in order to equalize the concentration on both sides of the membranes. So the net flow of water stops once both concentrations are the same. And so we talked about this in terms of blood cells, and so know what happens in a hypotonic, hypertonic, and isotonic solution, okay? All right, concepts from chapter 10. Started talking more about reactions, and we talked about how in a reaction, molecules must collide, have a certain orientation, and have enough activation energy in order for the reaction to happen. And then we talked about different things that can influence the rate of a reaction. So concentration, right? Higher concentration increases the rate of reaction. Higher temperature increases the rate of a reaction. And presence of a catalyst increases the rate of a reaction. And we talked about reversible reactions. So reactions come to equilibrium when the forward rate equals the reverse rate. Okay, it doesn't necessarily mean that the concentrations are the same, but it does mean that the concentrations stop changing when you get to equilibrium, okay? And then we talked about equilibrium constants, right? So the equilibrium constant expression for any given chemical formula is going to be the products raised to the power of whatever coefficient it is, divided by the reactants raised to the power of the coefficient. And remember that you don't include solids or liquids in this. You only include gases and solutes. So that would be aqueous phase in the equilibrium constant expressions. So as an example, the equilibrium constant expression for this reaction is just CO2, right? You don't divide it by the concentration of calcium carbonate because it's a solid, okay? If you had something like this, then you have carbonic acid divided by CO2. Water is not included because it's a liquid, right? You probably practiced these a few times in the homework by now. Okay, so yeah, be able to use Kc, know the meaning. So if Kc is about 1, that means the amount of products and reactants are about equal. If Kc is large, that means there's more products. If Kc is small, that means the equilibrium favors the reactant side. And then be able to use Kc with concentrations and numbers to do calculations. Then we talked about disturbing equilibrium. This is Le Chatelier's principle. So we identify which side of the equilibrium is stressed and then how that shifts to relieve the stress. So know what happens to a reaction at equilibrium if you add or remove reactant or product, add or remove heat. Again, this is going to depend on if it's exothermic or endothermic. And then what happens if you change the volume, okay, is another thing we talked about. All right. So here's a little kind of a practice question, a little review. So if we looked at this reaction at equilibrium, we can see it's an endothermic reaction because heat is a reactant. If we added NO, okay, so we increase the products, that means the reaction is going to shift towards the left, okay? And then if we added NO2, that's a reactant, it's going to shift towards the right. If we lowered the temperature, that'd be the same as removing reactants. It's going to shift over to the left. Anyway, my arrows are going to get confusing as I go along here. We've talked about this though a few times, and hopefully your homework has led you through some practice problems with these. Okay, chapter 11, we just kind of started this. This is acids and bases. So there's only 2 lectures on acids and bases in the 3rd exam, but they're important ones. So we talked about Arrhenius acids versus Arrhenius bases, how acids produce H plus in solution, right? It's an electrolyte that produces H plus, and Arrhenius bases are electrolytes that produce OH minus. Bronsted-Lowry acids, donated proton, and Bronsted-Lowry bases accept protons. And then how to determine if something is a strong or a weak acid, or a strong or a weak base, right? So there's strong acids that you need to memorize, and weak base and strong bases that you need to memorize, and then everything else is going to be either a weak acid or a weak base. So know the 6 strong acids, the strong bases, converting from chemical formulas to names, from names to chemical formulas for acids, and then identifying conjugate acid-base pairs in an acid-base reaction. So here's just a review slide of what we talked about before with naming acids. I'll let you kind of go over that or review that lecture if you need help with those. And make sure you practice doing this. So if you don't have your polyatomic ions down yet, you really need to start nailing that down. It's not going away for this test, and it's not going away for the final. So you need to know the names of the polyatomic ions, or else you won't be able to name the acids, right? Because the acid rules that I give you in this previous slide all depend on if you actually know how to name the polyatomic ions anyway, okay? So again, to name the acid, you just look at the name of the anion. So in this one, carbonic acid, right? The anion is carbonate, okay? And then ate is replaced with ic acid for when carbonate is in the acid form. Then we talked about Ka and Kb, which is just an equilibrium constant expression, but for acids and bases, and how the larger, if Ka is big, then it's a stronger acid. If Ka is low, then it's a weaker acid. If Kb is big, it's a stronger base. If it's low, it's a weaker base. And then you can actually relate these two using this equation. So you can go between Ka and Kb for conjugate acid-base pairs using this equation. And that idea shows you that Ka and Kb are inversely related, or strengths of acids and bases are inversely related. For example, hydrogen sulfate is a decently strong acid, but its conjugate base is going to be very weak. So you can see that relationship between those, okay? All right, that should be the material for exam 3. Kind of crazy to see all the things we've done so far summed up like that. Hopefully that gives you more direction as you're studying for the exam, what to focus your efforts on. And then I think we only have like 4 or 5 more lectures until the final. Don't worry about that right now. Just take exam 3 and worry about that. And then we'll get the final done after that. So if you have any more questions on exam 3, how it's structured, or any questions on these topics that you want to go over, come to office hours with me or Promoda or any of the other virtual, they're not virtual, well, they're real TAs, but they're virtual like TA tutorial lab that we have set up that you can go to as well. So alrighty, sounds good. We will see you next time.